I'm going to talk about water transport in boron nitride nanotube membranes, as you can see from this video over here. Now, before I start talking about boron nitride nanotube membranes, a bit about why I'm talking about boron nitride nanotube membranes. So lots of people in lots of countries are going to be without water in the near future. Desalination is the way out of it, and is mostly done using reverse osmosis membranes. Efficient new RO membranes can be made using these new materials, aligned nanotubes of carbon and boron nitride. You need very small diameter nanotubes, less than 1 nanometer, a few angstroms, to be able to exclude these sodium and chloride atoms and all the other small molecules. And when you're talking about these very small systems, which are less than a nanometer, you obviously need something like molecular dynamics to try and simulate these. So that is what I do. I use molecular dynamics to study these systems. And so now, why boron nitride? If we look at this picture of the molecular structure of the CNT and BNNT boron nitride, one thing that you'll notice is that the BNN atoms of the boron nitride carry a partial charge, as the boron carries a small partial positive charge, the nitrogen has a small negative charge. And not only that, when this membrane is in contact with water, the membrane has a net negative charge. And what this net negative charge allows is that as soon as a charged particle having a negative charge comes close to the membrane, it experiences a repulsive force. And that means that boron nitride membranes can repel particles based not only on the size of the pore, but also on the charge. And as you can see, this graph shows that the particle, a charged particle, negatively charged particle, it stays further away from the boron nitride membrane than it does for a carbon nanotube membrane. And the other thing that this allows is that because now the repulsion is also being done by the charge of the membrane, you can have a larger pore, and a larger pore means you can have more water flow for the same amount of rejection. And we found that BNNTs, because we can use larger pores, we have up to 70% more water flow through a BNNT compared to the CNT for the same amount of rejection. So very clearly, BNNT is a material worth looking into. But before we go into how a BNNT rejects a particle, there are some more basic questions about BNNTs which have not been answered. And the most basic question is obviously, how fast does water flow through BNNTs? Does water flow through BNNTs faster than the CNTs, or is it slower? And if you look at literature, there's enough supporting evidence on both sides. I mean, you can cherry pick your data, and if you look at the papers on the left-hand side of the table, then you can say that BNNTs conduct water equally or even better than CNTs, versus the papers on the right side. They show that BNNTs perform worse, that water flows more, slower in BNNTs. Clearly, there's something going on, there's some discrepancy, and it needs to be looked into, and we need to answer how fast does water actually flow through BNNTs. So before we can go into comparing BNNTs with CNTs, we need to come up with a metric to compare. And across literature, there are many different kinds of metrics. There's slip length, there's volumetric flow rate, there's friction coefficient, there's mass flow rate, there's mass flow rate and pressure drop. So the problem with all of these measures is that some of them, they need to be extrapolated, they cannot be directly taken from simulations, they cannot be directly taken from experiments. So what we decided to do is we decided to go with something called the flow resistance, which is simply the pressure drop divided by the mass flow rate. So when we go with this, both the pressure drop and the mass flow rate are easily available from both experiments and simulations. With the mass flow rate, you don't need to worry about viscosity, density, all of that, which you need to know in order to calculate the other parameters like slip length, friction coefficient, and all of those stuff. So we use the resistance, flow resistance, simply defined as pressure drop divided by the mass flow rate, right? Now that we have a measure, can we just as a guideline estimate what this measure what this K1 should look like numerically, what value it should attain, and just as a guideline, nothing else. So if you look at a problem, our problem is essentially a flow entering a tube and going out of it. This is a very basic problem. And so there's two places where the resistance, the fluid can encounter resistance as it is entering the tube and as it flows through the tube, right? As it is entering the tube, we have this term from the Weisberg equation, which gives the resistance, and we call this the end resistance, K1, and it's given by the Weisberg term. And for the resistance within the tube, we call it K2 or K2 prime when it's divided by the length, for a unit length, and that's given by the Hagen-Poiseuille equation. Together, if we add up K1 and K2, we get the entire resistance of one nanotube, of the membrane, one nanotube. And we can, expand it to how many nanotubes we have. So essentially, the total resistance can be divided into two components, the end resistance and the nanotube flow resistance. And there are formulas or equations for some guideline values for the both of them. Right. Now, a bit about how we studied this problem. We used molecular dynamics, used the TIT4P 2005 model. I don't think I need to go much into the details of this. I used LAMPS, the MD software. Now, coming to the setup. So now remember, we have to calculate two resistances. We have to calculate K1, the end resistance, and K2, the nanotube flow resistance, right? So we have two unknowns. We take two different kinds of setup. So in setup one, we have a short nanotube connected to ends on both reservoirs. And in setup two, we have a very long nanotube with periodic boundary conditions on both ends. So it's essentially modeling an infinite nanotube. Right, so now we have two different setups, one which has end resistances and one which does not have end resistances. And then it's a simple linear set of equations. We can calculate K1 and K2. Because again, remember, from MD, we can only get the total resistance. We can get the mass flow rate, the total mass flow rate, and the total pressure drop. So we can only get the total resistance. And when we have these two set of systems, we can then calculate K1 and K2, that is the end resistance and total resistance individually. Right. So now we look at the end resistance for BNNTs and CNTs. And what we see is that all of them pretty much lie close to each other. BNNT, they have roughly similar behavior, and the black line shows the expected values from the Weisberg equation. So all of them lie close to that. They behave similarly. But if we zoom in a bit, what we'll see is that the BNNT, the plain BNNT, has a slightly higher resistance than the CNT, versus the BNNTH has a lower resistance. What I mean by BNNTH? By BNNTH, I mean those BNNTs where the ends of the boron nitride are terminated with hydrogen. So when you do not terminate the ends of boron nitride with hydrogen, you have this spike in the end resistance, which you see in the blue bar, right? And the reason why this is important is that because of the way we typically model these membranes in MD. Now, when we model these in MD, what we have is a 2D sheet in which we cut a hole and then place a nanotube perpendicular to the sheet centered on the hole. Now, this is fine if you have something like a carbon nanotube, but if you have something which has charges on it, like boron nitride has, what you end up with are these improperly terminated edges where water molecules like to stick, and you end up with that high resistance that you were seeing. So you can see here there's a spike in the density in front of the membrane, and the trajectories of the particles which you see in this figure, it shows that there are water molecules which are stuck next to the edges, and if you hydrogenate it, then that seems to disappear. So this is an artifact which arises only because of MD and the way things are set in MD. And using hydrogenation, setting partial charges to 0 around the pore, or creating a continuous sheet as it is expected. So in real experimental setup, we expect the sheet to actually be continuous and this not to be there. This thing might disappear. Okay, right. So far we have discovered, we have discussed the end resistance, K1. Now we are going to discuss the nanotube flow resistance, which is the resistance inside the nanotube, K2. But before we discuss that, a bit about the partial charges. Now, I've said that boron nitride has partial charges, but what partial charges we should put on the BNN atoms, that again is confusing in literature. There are papers which use 0.3, a value of 0.3. There are papers which use a value closer to 1. So you have these two sets of charges. We tried to carry out a small charge equilibration using some parameters from some literature, and we found a charge which is closer to 1, plus minus 1. But anyway, we wanted to see how this variation of charges actually changes the nanotube flow resistance, which is K2. And so here we do that. And if you look at the blue lines so this is K2, the nanotube flow resistance. And if you see here that as we decrease the partial charges, the resistance keeps on falling. At no charge, the resistance is in fact less than carbon nanotubes. Conversely, as we increase the partial charges on the boron nitride nanotubes, the nanotube flow resistance increases, K2 increases, right? So, and this is something which is expected. These other guys have found this true for carbon nanotubes. They artificially put charges on carbon nanotubes, and as they increase the charges, the interactions with water increase, and you find that the resistance increases as the charge increases. And this difference is almost 2 orders of magnitude at the smallest diameters, which is what you intend to use for desalination purposes. The next thing which we had was an experimental result. So we had some people at the University of Bath carry out some experiments with the water flow through boron nitride nanotubes. They had much wider in diameter nanotubes than we did, because MD is obviously very computationally expensive. We can't go into this regime. But it again shows that the experimental results show that the BNNTs, they have resistance which is generally higher than the CNTs, and also that if the no-slip equation, that is the Hagen-Purcell no-slip equation was plotted, then the BNNTs actually have resistance which is slightly higher than that, which indicates that there may be some defects within the BNNTs. And if we place our MD simulation results over here, then again, it's the similar trend to show. Now, this again is the total resistance, not K1, not K2, but the total resistance, because obviously from experiments, as from simulations, we cannot individually get K1 and K2, we can get the sum total of them, right? Okay, so far we have seen that MD and experiments both have shown that BNNTs have a higher resistance than CNTs. So now we go back into so now we go back into literature and try and see why literature was showing that discrepancy. Some studies showing BNNTs better, some studies showing CNTs better for conducting water. And so I've plotted the resistance which I found from the literature, where there was flow rate, I've taken flow rate, where there was some other parameters. So I've tried to combine all of that into resistance and arranged it against diameter. So what you see here is that this is the total resistance from all the literature that I found. And this total resistance actually lies on the Weisberg curve. Now, Weisberg curve only predicts the end resistance, the resistance at the entrance of the nanotubes. But the total resistance from all of these papers in literature, it lies close to the Weisberg curve. And what it actually suggests is that the literature, what it is giving is actually not the effect of the nanotubes itself, but just the effect of the ends of the nanotube. Now, most of the literature that I found use nanotubes which are shorter than 20 nanometers. And so what I've done here is I've plotted the nanotube flow resistance, which is the K2 component of it, for a 20 nanometer nanotube. And what you find here is that the K2 component at 20 nanometer is an order or 2 orders of magnitude smaller than the K1 or the end resistance component. And so it does not show up in these literature studies, even though the K2 for BNNTs is an order of magnitude higher. So that is being completely hidden by the end resistance. So the nanotube flow resistance, the K2 component, is being hidden by the K1 component, the end resistance. But if we were to plot it with length versus length, then you'll see that as soon as the nanotube lengths start to increase and we reach into the micrometer range, the tens of micrometer range, which is where all the experimental membranes are. Now, these are very long nanotubes. And at these very long nanotube lengths, it is the K2 which starts to dominate. And your K1 goes, it becomes negligible. So you have a situation where the experiments, they have these long nanotubes where K2 is dominating. The simulations, they have these short nanotubes where K1 is dominating. And so this creates grounds for this discrepancy to arise. And as we have seen previously, the K2 for BNNTs is unquestionably higher than for CNTs. And this kind of shows that as far as practical experimental scale membranes are concerned, you have BNNTs always having a higher resistance, or conversely a lower flow rate as compared to CNTs. So there's conclusions. Disagreements in literature might have arisen because literature considers, specifically MD simulations, they have used very short nanotubes where the total resistance or the flow rate is dominated by the physics of the ends, not the nanotube. The most important factor which governs the end resistance is obviously how you have modeled the end and how accurate it is to experimental setups. Nanotube flow resistance, depending on what you choose your charge to be, it can be very high or it can be very low. Because our experiment showed that the end resistance was higher than CNTs, we kind of tend to be on the side of higher partial charge for the BNNTs. High partial charges make it likely that the BNNTs will have a higher resistance. And so when we are comparing MD simulations with experiments, or even MD with MD, we need to keep in mind that how long the nanotubes are and which of these resistances are dominating. And I mean, not only that, the idea that we should be comparing resistances, I think that it's important when we're talking about nanotubes instead of other variables like slip length or something like that, which would need some assumption of viscosity or density or something like that within the nanotube. And finally, the separation of the end and the nanotube flow resistance, that is K1 and K2, it says that even if we heavily modify the ends of the nanotube for a practical membrane, it won't make much of a difference on the flow rate, because flow rate in a laboratory scale membrane, it would be dominated by the nanotubes, not what's happening at the ends of the nanotube. Right, so that's me. Those are the two papers in which you can find what I've presented here. Any questions?